Okay, this is part 1 of lesson 5 of unit 6, the fundamental theorem of calculus and definite intervals. This lesson is going to connect what we've done with area under the curve with definite intervals, our properties of definite intervals, and how to find the antiderivative, and tying it all together to the fundamental theorem of calculus. Okay, so we have gone through our differential calculus section, which was our tangent line problem, and we have started into our integral or area problem. Now what we're going to look at next is how do we connect the two together. And the idea is that differentiation and integration are inverse operations. So we used in the previous lesson how the fundamental theorem of calculus part 1 defines new functions. So now let's take a look at this again and connect it now to our fundamental theorem of calculus part 2. So the first part of the fundamental theorem of calculus told us if we had a continuous function on a closed interval a, b, then g of x is equal to the integral from a to x of f of t dt. And it is continuous, g of x is continuous on the closed interval, and it's differentiable on the open interval, and that derivative is equal to our f of x. So we also saw how we can use the Leibniz notation with the df dx to get our f of x. Okay, so what we're saying is that we're defining a new function as a definite integral of another function f. So what we're going to connect now with the part 2 of the fundamental theorem of calculus is how we can compute these without having to find an area under the curve or the rectangle, left and right rectangles, or the trapezoid method. So what we want to remember is from our differential calculus is that f is a rate that our capital F is changing, and that little f is the derivative of capital F. And we know that if we take the integral from a to b of little f of x dx, that's going to represent the total net change in capital F on our closed interval. So here's how this works with the second part of the fundamental theorem of calculus. So as we look at this continuous function on the closed interval, the antiderivative can now determine the area in this way. We take the antiderivative, then we compute the value of this antiderivative at the endpoints and subtract them. So we can say the definite integral of a function over the closed interval AB is equal to the net change or the displacement in the antiderivative of little f over the same interval. This is known as the evaluation theorem, and we'll be using this quite a bit. Okay, so when we apply the fundamental theorem of calculus, what we want to remember is that we are going to use this notation that when we're ready to evaluate it, we use the capital F of x, and then we put a line with a to b. Sometimes you also see, like, people will put, and I do this sometimes, like the end part of a bracket like that as well. Okay, so both notations are correct. Now, one thing that isn't explained well in this section is how do you find the antiderivative? So for a polynomial, it's pretty simple. So if our f of x, I'll just put this right here, is x to the n, our capital F, which is our antiderivative, is going to be, we're going to put that power back, because remember we subtracted 1 from our power, and we brought that power down to multiply. So now we're going to do the opposite and divide. So that's what we're going to do for each term. And the other antiderivatives we're going to find in this section are our calculus ones, the basic ones like cosine, sine, tangent. So we're going to go from there. Okay, so as I do some of these, I think it'll become more obvious. All right, so I'm going to do a couple, and then I'll have you guys do a couple. So for the first one, we're finding the integral from 1 to 2 of x squared minus 3 dx. So I'm going to take the antiderivative of x squared. So I'd add 1 to the 2, so that gives me x to the third. But I'm going to divide by that 3 as well. So the idea is if you go to take this derivative, you should get your x squared back, which I will, minus 3x, because if I take the derivative of 3x, I'll get 3. And then I'm going to evaluate this from 1 to 2. So I'm going to have 2 to the third over 3 minus 3 times 2. That's evaluating it at 2. And then I'm going to subtract the value at evaluating it at 1. I'm showing all the steps here since this is our very first one. So then what we get is we get 8 thirds minus 6 minus 1/3 minus 3. And simplifying this, we get negative 2/3. Okay, so I'm going to do part B. And I want to first remember some of my properties of integrals so I can pull the 3 out, because that's a constant. And remember, the square root is x to the 1/2. So I can use my antiderivative rule for this since it's a power. So this is going to equal 3 times. Adding 1 to 1/2, I get 3/2. So dividing by 3/2 will be the same as multiplying by 2/3. And then this is going to be evaluated from 1 to 4. Okay, because remember, this would have been divided by 3/2, just like we did here in letter A. So it'll end up being flipped over to be the 2/3. Okay, so that's where I got the 2/3 from. Okay, so now I can evaluate it at these endpoints. So I'm going to have 3 times 2/3. I can even pull the 2/3 out. Let's go ahead and do that. So that's just going to give me 2/3 of 3 is just going to be 2. And then I'm just going to have 4 to the 3/2 minus 1 to the 3/2. So I'm going to get, that's going to give me 2 times 8 minus 1, so 2 times 7, so I get 14. Okay, so for the next one, what I want to do is we aren't ready to do our chain rule yet. We'll get there, but I'm just going to multiply this out because it's just a polynomial. So from -1 to 1, I have 4x squared minus 4x plus 1 dx. And now I can find the antiderivative of each of those terms. So I get 4/3 x to the third minus 2x squared plus x. And I'm going to evaluate this from -1 to 1. Okay, so doing that, I'm going to have, putting 1 in there, I get 4/3 minus 2 plus 1. And then from that, I'm going to subtract -4/3 minus 2 minus 1. So simplifying these a little bit, the first parenthesis becomes 8/3. The second one, I get, when I put this all together, because I'm going to have the 8/3 from here with that 4/3, and then I have a -1 and a -3, but that's a double negative there, so I get plus 2. And so simplifying this, I get for a final answer 14/3. Okay, so the last one I'm going to demo here is the sign. Now remember, we can divide using our properties. We can do this term by term. Now you don't have to write it out this way, but I'm going to show you what I'm doing to show our integral properties, because this isn't really a polynomial. But that's what I'm doing. I'm going to do each one term by term. Now, the antiderivative of sine is going to be negative cosine. Because remember, the derivative of cosine is negative sine, and I'm missing a negative sign, so I need to include that negative sign there. And then plus the antiderivative of 1 is going to be x, and I'm evaluating this from 0 to pi, so I'm going to get minus the cosine of pi plus pi, and then from that I'm going to subtract negative cosine of 0 plus 0. So simplifying this, this is going to be positive 1 plus pi, and that's going to be negative 1, negative, negative makes a positive 1, and so I get 2 plus pi. And you can just leave your answer like that. Okay, so as far as in the next few go, just to give you some hints here, the last two, you're going to rewrite that as the integral from 1 to 8 of, and you can put the square root of 2 out front, of x to the negative 1/2 dx. And for the last one, you want to divide that out of both terms. So you're going to have the integral from 1 to 4 of x to the 1/2 minus 2x to the negative 1/2. Whoops, that's not exactly in the right spot. Dx. So go ahead and pause here and try these two and then check your answer. Okay, there's the answers to the last two. And again, as always, if you have any questions, we can go over these in class. Okay, moving on and going through some of the terminology that comes up on the AP test. Example 2 talks about total change concepts and explaining what the parts of the integral means in the real world situation that were presented. So if f of t represents, if you notice it says the rate at which your 401k changes in value over the month of January, units of f of t, little f of t, is dollars, that's a terrible dollar sign, is dollars per day. And dt is days, because we're talking about the change per day. And f of t dt is going to be money, because you're going to multiply dollars per day times days. So if we're going from 1 to 31, f of t dt represents the total change in your 401k dollars. For the month of January. All right, part B says, if R of t represents the rate at which your pizza changes temperature in a 475-degree pizza oven 5 minutes after the pizza has been placed in the oven to cook, then if we're looking at the integral from 5 to 20 of R of t dt represents the total change in the temperature of the pizza. And of course that's in degrees Fahrenheit, because we were working in Fahrenheit, from 5 minutes to 20 minutes. Okay, part C. You and your friend, let me see if I can get these all on here. I don't think I can get the last one on. We'll do the first 4 there. You and your friends are planning to buy a ticket for your favorite music group, the Newtones. Get it? Newtones. Everyone wants to hear their latest hit, Why Integrate? If A of t represents the rate, so obviously it's something we're going to integrate, the rate at which the students are arriving at the ticket window, and P of t represents the rate at which they buy their tickets and enter the concert, then the integral from 1 to 5 of A of t dt represents the number of students arriving in the line. Let me write that part before I get to the limits of integration. Arriving to get in line from 1 to 5 minutes. And our integration from 1 to 5 of P of t dt represents the number of students that buy their tickets. And of course, it's from the same time frame. And of course, they leave the line. That's important to say, because once you get your ticket, you leave the line. And I'm putting that there for the next parts. Okay, and so if we're taking A of t minus P of t, we haven't integrated, so this is a rate. So this is the rate, oops, that's terrible. It's that glitch again I still have, is the rate at which the line is either growing, depends on how fast they are, or shrinking. Okay, and then if I integrate from 1 to 5 of a of t minus p of t dt, that represents the total line, the total change in the length of the line. During 1 to 5 minutes. Okay, so now it says recall that velocity v of t represents the velocity where the position direction is to the right. So velocity is the rate at which position changes, because these come up a lot: velocity, position, and acceleration. Okay, so the integral from 5 to 50 of v of t dt represents the total change in position on our closed interval, which has a special name in math called, and we call that our displacement instead of distance or position. Likewise, a of t, if we're going the other way, is the rate at which the velocity is changing. Okay, then in part 2, we're going to do our special cases and what happens when we change the limits of the integration, and go from there looking at piecewise and a calculator. So these are some special cases that we're going to look at. But this is the basics of the fundamental theorem of calculus and the antiderivative. So we will stop here and continue in the next video.